So now let's get back to what we're doing for the interacting gas. Okay, so I got to get my iPad sharing here. Share iPad via cable. And there it is. Okay, great. So you remember how we left things in the last class, right? That we worked out this van der Waals theory for the interacting gas. And that theory was based on putting two kinds of effects into the interaction between molecules. Right? So one effect is that there's some kind of hardcore repulsion, right? That the molecules can't push closer than a certain distance. Right? And the other effect is that there's some long-range attraction. When the molecules are far away, they feel a little bit of an attractive potential energy pulling them together. Right? So I put them into the theory, and my derivation was not really rigorous. It was a little bit of hand waving, as we say. But in the end, it did give a specific expression for the Gibbs free energy, which is this thing. Okay. And then he said, this is the Gibbs free energy for a system that has fixed pressure and variable volume. And so the system is able to choose its own volume, like the ideal gas that can choose its own volume. And so then we asked, well, what volume does it choose? So we figured that out by setting the derivative of the Gibbs free energy with respect to volume equals 0. Right? And that gave us this equation right here, which is called the van der Waals equation of state. Right? And you can see that this is a modified version of the ideal gas equation of state, which is just pressure times volume equals NKT. Right? So this is some improvement on the ideal gas equation of state. Right? The ideal gas equation of state is assuming that there's no interaction between molecules. And now we suppose there is some interaction, and we have two parameters to describe the interaction, these coefficients A and B. Okay, so when A and B are both 0, we get the ideal gas. When they're not 0, when there's some positive numbers, we get the interacting gas. So there are a couple of different points of view that you can take on an equation like this. Okay, so one perspective would be, say, the perspective of a chemical engineer. Okay, so suppose you're designing some big chemical factory, and you really need to know what's the relationship between the pressure and volume and temperature of a gas that you're working with, because you want to make sure that your factory is not going to explode. Okay, and so you would want to use an equation like this one. Okay, this van der Waals equation. Okay, and so the numbers for A and B, would be different for each kind of gas, right? So you could look up for carbon dioxide, for example, what are A and B, right? Or for argon or nitrogen or whatever gas you're working with, right? And so you'd look up the A and B numbers for the gas that you want, and then you would know the relationship between pressure and volume and temperature and use that for your design. Okay, so it will give you more precise predictions than just using the ideal gas equation. But okay, there's more that we can do that goes beyond these numerical corrections. Okay, and what I want to show you is how we can actually look graphically in some plots to see what are the minima of G, right, as a function of volume. Okay, so this is something that we can figure out, right, for any particular numbers of A and B. Okay? So I'm going to take this G and plot it and look for the minima. Okay? And to be specific, let me do a little bit of algebra just to get something specific to plot. Okay, so I'm going to take it and divide both sides by NKT. Okay, I think that's the same thing that we did previously in NKT. Okay, that's the same thing we did previously for the ideal gas, right? And that's a convenient thing to do because then these factors cancel, and then we can then say, let's look at a scaled volume, okay? So here, this is a V over N. Let's call that little v. So that's the volume per molecule. So little v is going to be capital V, the total volume, divided by the number of molecules, okay? And here, there's a V over N. So this is another little v. And here, there's an n squared in the numerator and an n in the denominator, right? So here, there's a little v in the denominator. Okay. So instead of, actually plotting G as a function of capital V, right? So I will plot this normalized G over NKT as a function of little v, that is the volume per molecule. So this total volume divided by n. Okay. And in order to make a plot like this, we need numbers for A and B. Okay, so I'm going to make an example where A equals 1 and B equals 1. Okay, now, really A and B are parameters with some units, right? As we talked about before, B has units of volume and A of energy times volume. Okay, so I will just say, whatever they are, I'll make up a new system of units instead of working in SI units, where the length is measured in meters. I'll work in some other system of units where the length is measured in the cube root of B. And there'll be some other energy units also. And so this will make just an example plot where, with those parameters. And then, of course, I can just change to another example plot with specific physical numbers of A and B for carbon dioxide or any other gas. Okay, so let me stop sharing the whiteboard and I will start sharing the Mathematica. Okay, you see the Mathematica, right? Okay, good. Okay, so here, first, in this Mathematica file, I have the Gibbs free energy for the ideal gas. Okay, so this is the sort of plot that we looked at a few days ago. Okay, and we could see that there's a certain minimum, and the minimum changes depending on pressure and temperature. Okay? So now let's do the same thing for the interacting gas. Okay, so I'll do it here in my nice fancy interactive plot where I have the adjustable sliders for pressure and temperature. Okay, so I'm starting off at a pressure that is 0.01 and a temperature that is 0.3 in these weird non-SI units where A and B are equal to 1. Okay. Now, the thing that I'm plotting is like this, okay? So this is the Gibbs free energy that we calculated. So it has the logarithmic term, it has this negative A over V term, and the positive pressure times volume term. So what can you see here? Okay, here at this pressure and this temperature, there's a minimum right there. Okay, so at a volume of, I don't know, 27 in these peculiar non-SI units. So this is similar to the minimum that would be calculated for an ideal gas. It's not exactly the same, but it's similar to the minimum that would be calculated for the ideal gas. Okay, now let's suppose we reduce temperature and see what happens to the volume. So I'm going to change the temperature slider and see what happens to the minimum. Okay, so I'm moving the temperature down, and we can see that the minimum is shifting to a lower volume. Okay? So that part is kind of like the ideal gas, okay? That we see that the minimum shifts to an ideal volume. So far, it's sort of similar to the ideal gas, but there are a little bit of corrections that might be important for a chemical engineer building a factory. Okay. Now, suppose we keep reducing the temperature, okay? We keep reducing the temperature, and we see minimum still shifts over, but there is this other funny looking feature over there, okay? It's not the minimum, but it's funny looking, it's interesting, okay? Now, let's keep reducing the temperature further. Now, let's see what happens to this funny looking feature. It's turning into another minimum. Okay? It's not the absolute minimum, but it is another local minimum of the Gibbs free energy. Okay? The absolute minimum is still over here. It's shifting smoothly. Okay? Well, okay, that's interesting. Let's keep reducing the temperature. Oops. Now we can see that this lower volume minimum keeps getting lower. It's almost the same as our first minimum. At a certain temperature, whoa, it is the same.
Question.
Please.
Is that still, I can't really tell because of just how small the graph is. Is that still continuous at that point, at that minimum? It looks really sharp.
It's really sharp, but it is continuous.
Okay.
Yeah, okay. Do I have a way to blow it up? I'm not sure.
Oh, okay. No, it's a good size. I
Oh,
just mean that
okay.
it just in general, it's just a simple graph kind of thing.
Yeah. It is very sharp, but yes, it is continuous.
Okay.
Good question. Okay. So at this temperature of 0.22 in these units, right, they're almost the same. If I keep adjusting it carefully, whoops, what did I do? Oh, I typed a letter O instead of 0. There, okay, 0.22, there it is. They're just equal, right? Now, there are two minima which are equally deep. Okay. Now let's make the temperature even a little bit lower. 219. Now this one is the lowest. Okay. So if we say the system gets to choose its own volume, now, it used to be choosing a number like 27, 26, 25, blah, 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 down to about 18, 17. Now, all of a sudden, it jumps to a number like 2, okay? So it is suddenly changing and choosing a very different volume than the one that it used to choose, right? It used to choose a big volume, like 20, and that was changing smoothly with temperature. And then all of a sudden, at a certain temperature, it jumps to a way smaller volume, like 2 or 1.8, something like that. That's where the minimum is, okay? And now, if I keep reducing temperature further, it stays at the lower volume. And maybe the location of the minimum changes a little bit, but not very much. Okay. So that means that the system is changing from the original high volume gas to something else that has a way smaller volume per molecule, right? Or high volume means low density, right? So it's changing suddenly from the original low density gas to something that has a way higher density. So we have to think, what is something that's sort of like a gas, but it has a way higher density than a gas? Okay? So that would be a liquid. Right? So here we are seeing that the phase that the van der Waals theory is predicting a phase transition from gas to liquid. So I can say, whoa, I discovered liquids. Or maybe I'm not the first person to discover liquids. Maybe that was like the first guy who fell in a lake. But that, I'm rediscovering liquids, right? So here we see a phase transition from the gas state to a liquid state, okay? So this is a big extra thing that comes from van der Waals theory, right? Maybe we thought this was just going to give us a few little corrections to what's the volume of a gas, but actually it's giving us this big new thing that we didn't have before. Now, this all was happening at a fixed pressure, okay? So a pressure of 0.01 in these weird non-SI units, okay? Let's try to see what happens if we repeat the whole thing at a different pressure, okay? So if we do it at a lower pressure, no, I said lower and I made it higher. Let's do it at a lower pressure, 0.005, okay? There's a lower pressure, okay? Now I will keep on doing this cooling and see what happens, okay? So I'll keep on doing this cooling and we see we are going to get this transition right about there. Okay. And now we see that the transition happens as it did before, but it's not at the same temperature where it was before, right? That previously it was at a temperature of about 0.22 in those funny units. Now it's at a temperature of like 0.19. Okay, so that is saying that at lower pressure, the transition between liquid and gas occurs at a lower temperature. Okay? And this is something which is actually familiar from everyday life. I mean, not everyday life in Ohio, but everyday life in cities at high altitude, like Denver, Colorado, right? And so, if you go to a high altitude, then water boils at a lower temperature, right? So we know that water boils at 100 Celsius when you're at sea level, right? But if you go to high altitude, then water will boil at a lower temperature that's less than 100 Celsius. So people who are cooking at high altitudes need to use different recipes because the temperature is different. So this transition is like that, right? So the change, right, when we go from low temperature to high temperature, right, this is boiling, right? This is the low volume phase. The liquid changes into a high volume phase, the gas, right? And so at low pressure, this happens at a lower temperature. We can also see that at low pressure, the difference in volumes is extra big, right? That now it's a jump from like 1.8 to 35, right? Whereas when we started, it was like a jump from 1.8 to 22. Now, what if we are at extra high pressure? Okay, so I'll make the pressure higher. I don't know, I'll do it way higher than we started. Okay, here's some high pressure. Okay, so now we're in a low volume, and I will increase the temperature and make it boil. So I'm increasing the temperature like this as I move the slider up. Whoa, I need to raise it to a pretty high temperature, a lot higher than it was before. Okay, so here's the transition, right? So at high temperature, it is, at high pressure, you need a high temperature to see the transition. And there's only a small jump in volume. Okay, so let me write these things down. Okay, so if we say low pressure, that means that there is a, low, let me say that the transition between liquid and gas at low temperature. And there is a big change in density. Okay? And then if we go to a higher pressure, then the transition between liquid and gas is at a higher temperature, and there is a smaller change in density. Well, instead, I could say a change in volume per molecule, which is like the reciprocal of density. Okay, that's interesting. Now, let's keep going to even higher pressure and see what happens. Okay, so let's make the pressure even, I don't know, way higher. All right. Now I'll vary the temperature to find the transition. There sort of is no transition there, right? Because the transition was when we saw two minima that become equally deep. And now there are no two minima. There's only one minimum. And so I'll write that down. There is no transition between liquid and gas. There is just a smooth change in the volume per molecule. So let's suppose we wanted to summarize these results by making plots of what happens to the volume as a function of temperature for different pressures, okay? And so I could do that by just changing temperature and pressure and writing down where's the minimum, okay? So I could say, you know, I'll write down in my notebook, there's this pressure, there's this temperature. What's the minimum? Okay, it's about 1.8, okay? And then I raise the temperature. Now the minimum is about at 10, okay? Now, here I was trying to be fancy and make Mathematica code that would actually find the minimum for me, okay? So this is the plot generated by this fancy Mathematica code, but it's not necessary. I could just make a table and then plot the numbers in my table. Okay, so here are several plots for the volume per molecule on the vertical axis as a function of temperature on the horizontal axis at fixed pressure. Okay. So these things, as a vocabulary word, these plots are called isobars, right? So the word bar is like barometer, it means pressure. So these are plots at equal pressure. So first, here is a low pressure plot there in blue, okay? What you can see in the low pressure plot, at low temperature, we are in the low volume state, that's the liquid. Then we hit this temperature and there's a sudden huge jump in the volume. That's because we're jumping from one minimum to a different minimum. Right? So there's a sudden huge jump in the volume, and then we're in the high volume phase. That's the gas phase. Right? So, and then the volume is pretty sensitive to temperature, right? In the liquid, the volume is not so sensitive to temperature. In the gas phase, the volume is very sensitive to temperature. So this is what happens at our lowest pressure. Now we go to a higher pressure. We get this sort of purple plot. Okay, so there's the liquid state. The liquid phase persists up to a higher temperature. That is, it boils at a higher temperature. Now there's a jump from liquid to gas, and then the volume increases with temperature in the gas phase. Okay, now there's the yellow plot. That's even higher temperature. Okay, excuse me, even higher pressure. So now the liquid stays until a higher boiling point, and then it boils, but there's not so much of a change. When it boils, the volume only increases a little bit. And then the gas is going to continue increasing in volume. Right? Now, what happens when we get to the green plot at a certain pressure, which I will calculate for you soon? Okay. In the green plot, we see that the volume is increasing, and it increases and increases, and there's never a jump discontinuity in it. Instead, there's just a single point where the slope is vertical, right? This plot looks like a function that just has one vertical point right there at the tip of my mouse, okay? And then it smooths out again and it continues to increase. Okay? This special point is the critical point, right? It has a behavior analogous to the critical point in the Ising magnet that we were talking about, where there was also a plot of the magnetic order parameter as a function of field, or kind of like this.
Excuse me. What is the value of this critical pressure?
I will calculate that soon. Okay, hang on just a moment. Okay, and then if we go to an even higher pressure, there is no more vertical slope. Okay, now we go along and the volume's increasing, and now it increases faster. There's some point of inflection, and then it increases slower. So there's a point of inflection here, but there is no vertical slope, right? That the slope is big, but it's not infinite. So this is what the sequence of isobars look like, right? This is a sequence of plots for the volume that you get by minimizing this function right up there, right? As a function of temperature for different pressures. Now, we could turn things around. Instead of varying the temperature at fixed pressure, we could vary the pressure at fixed temperature. Okay? So we could get a series of plots at fixed temperature, which are called the isotherms, right? So therm is like thermometer, right? It means temperature. So these are plots at constant temperature. So now this blue one is the low temperature plot. Okay? So at low temperature, when you're raising the pressure, right? At low pressure, you have a gas phase, and the volume is really sensitive to pressure. And then there's a sudden jump, right? As you raise the pressure at fixed temperature, you go from one minimum to another minimum. That's like what we could see here, right? If we're at a low temperature, and we raise the pressure, whoops, what do we do? If you're at a low temperature and you start off at a low, where am I doing? Okay, here. If you're at a low temperature, you start off at low pressure in the gas phase. And then you raise the pressure and the gas suddenly condenses, right, into a liquid, right? So it's like if I have a balloon and I gradually increase the pressure, right? So there's a balloon and I increase the pressure and I measure the volume, right? So as I increase the pressure, the volume is getting smaller, 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 boom. And it gets to suddenly a much smaller volume. So that's what's plotted here. I increase the pressure, the volume gets smaller, 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 boom, gets to a much smaller volume. At a higher temperature, the gas persists up to a higher pressure. But eventually, at a high enough pressure, there's a sudden transition where it condenses into a liquid. It's a smaller change, but there's some change. Even higher temperature, you go to an even higher pressure, and then it condenses into a liquid. At an even higher temperature, at just the right temperature, the jump goes away. And instead of a jump, we just have one point with a vertical slope at the tip of my mouse. And so the volume is very sensitive right around there, and then it gets smoother again. So now, in answer to Cheng's question, this is at a pressure, a critical pressure of 0.037 in these units. And that is at a temperature, which we can read off from this plot of 0.3 something in these units. And I will work that out. Excuse me, no, it's this one. It's 0.29 something in these units. I will work that out algebraically coming up soon. Now, we might want to make a three-dimensional plot that shows both of these things, okay? So here is a three-dimensional plot where this axis is pressure, this axis is temperature, and the vertical axis is the volume per particle at the minimum. Okay. What do we see from this? Okay. We can see that at low pressure and low temperature, there's a big jump between the gas and the liquid. Low pressure and low temperature, the gas has a really big volume, and the liquid has a really small volume. And there's a big jump when you cross that transition. But as we move up to higher temperature and higher pressure, at some point, well, the magnitude of the change, the difference between liquid and gas gets smaller, right? At high temperature and pressure, there's still this boiling transition, but the liquid and gas are not so different from each other. And eventually, when we get to a special point in the phase diagram, a special point on this plot, the critical point, the difference between liquid and gas just goes away. So now there's one special point where the difference goes away. And when we're out past that point, it's just a smooth variation in the volume as a function of temperature and pressure. what I want to point out to you is this is a lot like the three-dimensional plot that we had for the Ising model, right? We had a three-dimensional plot for magnetic order parameter as a function of temperature and magnetic field, right? And in that three-dimensional plot, we could see that sometimes there was a big jump between spin up and spin down. And sometimes there was only a little jump between spin up and spin down. And at the critical point, that jump just went to zero. And beyond the critical point, there's no jump at all. It's just a smooth change from one to the other. Here, it's the same story. This is the same kind of plot. Really, the main difference is that in the Ising model, there's a nice symmetry between spin up and spin down, right? That spin up and spin down are just reflections of each other, and magnetic field up and magnetic field down are just reflections of each other. Here, there is no such symmetry because there's no symmetry between extra high density and extra low density, right? Because high density and low density are really different from each other, okay? So the symmetry is gone. And so the boundary like this is not right along some axis the way it was before. But still, it's the same kind of structure for the three-dimensional plot. Now, you remember one thing that we did with the Ising model is that we looked at the plot from above, and then we just made the phase diagram, right, to identify for each temperature and each field what is our equilibrium state. Okay, so now we can do the same thing. Okay, so I can now make a plot looking from above to say what is the state as a function of temperature and pressure. So let me see if I can wrestle, whoops, it's turning the wrong way. See if I can wrestle this plot into the right orientation. Sort of like this. Okay, well, it's not perfect, but sort of good. Okay.
Color to graph.
Yeah. So what I want to show you, right, is that here you could say there's a phase diagram where pressure is on the horizontal axis and temperature is on the vertical axis, except it came out over on this side. Okay, but I can make the plot like this one. Okay, so here now I have pressure on the horizontal axis and temperature on the vertical axis. Okay. So up in this region, that is for high temperature and low pressure, we have a phase with a big volume, right? We can see it because we look this way. There's a big volume. That is the gas, okay? So I should label this region is gas. Can I actually type on it? I don't have a good way to type on it. Okay, this region is gas right there, okay, for high temperature, low pressure. And you know that, right? You know that gases form at high temperature and low pressure. Down here on this side of the boundary, we have low temperature and high pressure, and that's the liquid. And you know that because there's a low volume per particle. You also know that because in ordinary life, right, at low temperature and high pressure, you get a liquid. So we could type that in here. This gets labeled as liquid. Right? And so this is how I make the phase diagram, which is in figure 3.8 in the book, except that one has labels and this one doesn't. Now, as you go along the boundary, right, this is the phase transition between gas and liquid. And the jump between gas and liquid keeps getting smaller, 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 smaller. Oops, right here, the jump goes to 0. This is the critical point in the phase diagram. Okay? So it occurs at the critical pressure there and the critical temperature there, which I will calculate for you on Wednesday. Okay? So this is the critical point. And beyond the critical point, no more phase transition. You just have some smooth evolution between gas and liquid with no sudden jump. So you might ask, what do we call this thing? Do we call it gas? Do we call it liquid? Neither word is really right because it's just where these things are coming together. Okay? Instead, people use the word supercritical fluid. Okay, I'll type that. Supercritical fluid to mean what occurs out there. Okay, and so, you know, the word super means beyond, right? Like Superman is beyond an ordinary man, right? So supercritical is beyond the critical point. Now, one question that students often ask is, where is the border between supercritical fluid and gas, or between supercritical fluid and liquid? And the answer is, well, there isn't exactly a border, right? And so, you know, you could imagine, you know, what if you're a sailor on a ship and you're sailing down around the bottom of South America, right? So you start in the Pacific Ocean and then you go south of the bottom of South America and then you come up in the Atlantic Ocean, right? So you might say, where's the border between the Pacific Ocean and the Atlantic Ocean? And the answer is, there isn't really a border. You just go continuously from the Pacific Ocean to the Atlantic Ocean. And, you know, sailors probably have some convention about when do they call it Pacific or when do they call it Atlantic, but it doesn't really matter. There is no border. It's just a question of what you call it, right? But if you're in New York City and you say, what's this ocean, right? Well, it's the Atlantic, right? If you're in San Francisco and you say, what's this ocean? It's the Pacific, right? Because there's a big difference between Atlantic and Pacific when you're in New York or San Francisco, right? That's because there's a whole country of the United States of America in between, right? And so here, we know at low temperatures and low pressures what to call gas and what to call liquid because there's a phase transition in between. Right? But when we're up here, it's kind of arbitrary what to call things. They all just sort of merge into one another, okay? But, you know, our everyday lives are at low temperature and low pressure. And so for our everyday lives, there's a big difference, say, between liquid water and water vapor. Those things have hugely different densities and hugely different volumes per molecule. But, hang on just a second, but at there really is a critical point for water, and up at that critical point, there is not a big distinction between these things, and so you go smoothly from one to another to another. Okay, so Bijaya, you had a question, please. I can't hear you.
Okay, in the critical point, we have three states: solid, liquid, and gas will exist simultaneously. But in a van der Waals approach, we can only describe the phase transition from gas to liquid.
No, wait, pause. This is the critical point. That is different from the triple point.
Okay.
Right?
Okay.
You are thinking about the triple point where gas and liquid and solid come together. The critical point is a different kind of point from that. And
okay.
I'll talk about the triple point later on in the semester.
Okay, and okay, I have also other questions. Can you
Okay.
describe phase transitions from gas to solid directly? I mean, we have a substance like camphor, where there is no any intermediate phase transition from gas to liquid. There is a direct
I'm not ready to talk about solids yet. Later in the semester, I'll talk about solids. Okay, but yes, there can be a direct transition too. That's a different story, which you're ahead of me now. All right, I'm going to wrap up for today, and I'll be glad to answer any more questions. And then on Wednesday, I'll get to the calculation of where is the critical point algebraically. All right, so I'll see you on Wednesday. Any other questions for now?
I'm still trying to understand the physics of the appearance of the volume gap in pressure volume plot at a fixed temperature. So when there, when there is no attractions between molecules, when there is only a pressure compressing the gas, and there is only a temperature, or we can call entropy, to expand the gas, the volume changes continuously, right? When we increase pressure, or we can also say the distance between a molecule and its nearest neighbor decreases continuously, right? But when we add the attraction interactions into the system, then the distance between a molecule and the nearest neighbor decreases discontinuously when the temperature is lower than the critical temperature, right? So I'm trying to understand why, because in my understanding, the effect of the attraction between molecules and the effect of the pressure are quite similar. They're trying to compress the gas, right? But why
it's interesting. Yes, they both are trying to compress the gas. But you need the attraction, right? So you would not have the transition without the attraction, right? And so that's why you need both of the parameters A and B in the theory in order to get this, right?
Right.
And so, you know, when I first started to teach this stuff, I thought, maybe instead of presenting both A and B, I should present them one at a time and have just a theory with just B but no A, right? And or a theory with just A and no B, right? And what phase transitions would you get then? But the answer is you don't get any phase transitions. You need both of these effects in order to get the transition. I have I mean, everything that we've presented here is a mathematical reason why, but you're asking about more of a physical reason why. And I don't have a great answer. The best I can do is to say, when you have both of these effects, then there's a certain high density state which is particularly good, right? When you have both a combination of attraction plus hardcore repulsion, then it's good for the molecules to be a certain distance apart and not closer and not farther, right? Not closer, because if they were closer, they'd be bumping into each other and feeling the excluded volume, but not farther apart because they'd lose the attraction, right? And so, you know, the molecules are happy to have, to be at a certain distance apart, right? And so, you know, it would be like, you know, if you have a group of people, a group of friendly people, right, who are all, you know, in some big space like a football stadium, right? If they're friendly people, then maybe they want to sit together pretty close and leave a lot of empty space, right? And so that's because, you know, they want to be close to their friends, but they don't want to be actually just pushing into each other, right? And so there is a particular high density state which is strongly favored by the combination of the attraction and repulsion. Okay? And so that is what stabilizes the liquid at a particular high density. But the gas is also stabilized by entropy versus pressure at a much lower density, a big volume. Okay? And so then you might say, well, which is better, having the thing that's stabilized by entropy and pressure, the gas, or the thing that's stabilized by attraction versus repulsion, the liquid? So that makes two different kinds of minima. And then depending on pressure and temperature, one or the other might be more favorable. So that's my best hand-waving story that would go with this, this mathematics.
Okay, thank you.
So I have a question kind of off of what Cheng had asked.
Mm-hmm.
You had said that, you know, we need the variables A and B in order to have a phase transition.
Mm-hmm.
And so based off of that, that would mean that ideal gases can't have a phase transition.
Correct.
Okay, I guess
That's right. The ideal gas does not have a phase transition. The ideal gas just stays as a gas down to point, you know, 0.00001 Kelvin, right? I mean, the ideal gas never has any reason to do anything other than be a gas because there's no interactions, right? I mean, here we're leaving out quantum mechanics, we're leaving out interactions, everything else. So it just stays as a gas.